This video series is funded by Jewish Hospital Foundation, Norton Healthcare, and the United States Surgical Corporation. This tape is the second of two that describe the head and neck. In it, we'll look first at the facial muscles and the scalp, then at the brain and its surroundings, then at the nerves and blood vessels of the head and neck, then at the eye and the ear. We'll start by looking at the face. Some important parts of the face, the nose and the orbit, are covered separately in these two tapes. In this section, we'll focus on the facial muscles, which produce the movements of facial expression. We'll go from above down, starting with the muscle that closes the eye, the orbicularis oculi. All this is the orbicularis oculi. It surrounds the opening between the upper and lower lids, the palpebral aperture. Orbicularis oculi has an inner or palpebral part and an outer or orbital part. The palpebral part is extremely thin. The orbital part is more substantial. Orbicularis oculi arises medially from this underlying structure, the medial palpebral ligament, and from the bone above and below it. Its fibers pass above and below the palpebral aperture, joining with each other here. When the palpebral part of the muscle contracts, the eyelids close gently. When the whole muscle contracts, they close tightly. Opening the eye is caused by elastic forces acting on the lower lid and by a more deeply placed levator muscle acting on the upper lid that we'll see later in this tape. Now we'll move down to look at the muscles around the mouth and the nose. The opening between the lips, the oral commissure, is surrounded by the orbicularis oris muscle. Here's part of it. The orbicularis is joined and overlaid by several other facial muscles, which we'll remove from the picture for a moment. Here's the orbicularis oris by itself. Its more superficial fibers encircle the oral commissure, some of them arising from bone here. Its deeper fibers are continuous with those of the buccinator muscle, as we saw in the previous tape. The action of orbicularis oris is to close the oral commissure and press the lips together. The deep hollow here between the buccinator and masseter muscles is filled with this buccal fat pad, which is continuous with the fat that covers the front of the cheek. Now we'll return to the picture all except one of the muscles that pull on the orbicularis oris. Pulling on it from above and behind is the zygomaticus major, which arises from here on the zygomatic bone. Pulling on it from behind is the risorius muscle. We use both these muscles when we smile. Pulling on the orbicularis from above are zygomaticus minor, absent in this instance, levator anguli oris, and levator labii superioris. These arise from here on the maxilla. Together, they raise the upper lip. The most medial corner of levator labii superioris, which goes by this very impressive name, attaches to the alar cartilage of the nose. It does this. Here on the side of the nose is the nasalis muscle. It helps to wrinkle the nose. The three muscles that join the orbicularis from below are quite hard to tell apart. They're depressor anguli oris, depressor labii inferioris, and mentalis. The last two run into one another and are embedded in this mass of fat and fibrous tissue which forms the prominence of the chin. These three muscles arise from here on the mandible. Between them they pull the lower lip downward and pucker the chin. The last muscle we'll add to the picture, the platysma, lies partly in the face but mainly in the neck. Here's the neck as we saw it in the last tape, without the platysma. Here are the sternocleidomastoid muscle, the infrahyoid muscles, and the digastric muscle. Now we'll add the platysma to the picture. All this is platysma. It lies within the subcutaneous fascia of the neck. Its lowest fibers extend below the clavicle, onto the chest. Platysma has a free posterior border here, and a free anterior border here, near the midline. Most of the fibers of platysma insert here, along the border of the mandible, but its more posterior fibers cross the mandible and insert into the orbicularis oris complex. The platysma pulls the corner of the mouth downwards and backwards, producing these ridges beneath the skin. Now we'll move on to look at the scalp. To understand the scalp, we'll start with a dissection in which all its layers have been removed, exposing the skull. The dome of the skull, known as the calvaria, is formed by bones that we've seen in the previous tape. The frontal, parietal, and occipital bones, and on the side by the squamous part of the temporal bone. The temporal bone is covered by the investing deep fascia of the temporalis muscle. Overlying the calvarium is a layer of loose connective tissue, the areolar layer. It overlies the deep temporal fascia too. The areolar layer separates the bone from the next layer that we'll add, the assembly of structures known collectively as the epicranium. The epicranium is formed partly by tendon, partly by muscle. To see it better, we'll add all of it to the picture. Over the dome of the skull, the epicranium is formed by a sheet of tendon that's known as the gallia, or gallia aponeurotica. Two muscles are attached to the gallia. In front, the frontalis, and behind, the occipitalis. The occipitalis muscle arises from here on the occipital bone, above the superior nuchal line. It inserts into the gallia. The frontalis muscle arises from the gallia and inserts into the skin of the lower part of the forehead, close to the eyebrow. These two muscles produce important movements of facial expression. When occipitalis and frontalis act together, the eyebrows rise. When frontalis acts by itself, the forehead is pulled downward in a frown. The full effect of a frown comes from the added effect of these not very separate muscles, depressor supercilii and procerus, and by the more deeply placed corrugator supercilii, which pulls the eyebrow medially, causing these vertical wrinkles. On the side of the head, the epicranium is formed by this area of dense connective tissue, the superficial temporal fascia. In some individuals, as in this different specimen, the epicranium includes the vestigial auricularis muscles, which can move the external ear. Now we'll add the more superficial part of the scalp to the picture. Firmly attached to the epicranium is a layer of fibrous tissue interlaced with fat. Above this is the hair-bearing skin of the scalp. These are the hair follicles, which extend through the thickness of the skin. That brings us to the end of this brief section. Now, let's review what we've seen of the facial muscles and the scalp. Here's the orbicularis oculi, its palpebral part, and its orbital part. Here's orbicularis oris. Here are the risorius, zygomaticus major, levator anguli oris, levator labii superioris, and nasalis muscles. Here are the depressor anguli oris, depressor labii inferioris, and mentalis. And here's platysma. Here's the areolar layer of the scalp. Here's the epicranium, consisting of the gallia, the frontalis and occipitalis muscles, and the superficial temporal fascia. Here are the procerus, the depressor, and the corrugator supercilii. That brings us to the end of this section on the facial muscles and the scalp. In the next section, we'll move on to look at the brain. In this section, we'll first take a brief look at the shape of the brain and its main parts. Then we'll look at the cavity that contains it and the layers of tissue that surround it. Then we'll return to the brain itself and look at it in more detail. Here's the brain. Much the largest part of the brain is the cerebrum. The cerebrum is partly divided in the midline into two cerebral hemispheres. Below the cerebrum, and separate from it, is the smaller cerebellum. The cerebrum and the cerebellum both grow out of the brainstem. The brainstem becomes continuous below with the spinal cord. The brain is contained within the cranial cavity. Here's the cranial cavity in a dry skull. It's almost the same shape as the brain. As we saw in the last tape, two big steps divide the floor of the cavity into three parts. The sphenoid ridges separate the anterior cranial fossa from the middle cranial fossa. This part of the cerebrum, the frontal lobe, occupies the anterior cranial fossa. This part, the temporal lobe, occupies the middle cranial fossa. The petrous temporal bones separate the middle cranial fossa from the posterior cranial fossa. The posterior cranial fossa contains the cerebellum and the brainstem. Here's the foramen magnum. Now let's see how the cranial cavity looks in the living body. The cranial cavity is lined throughout by this layer of tough, shiny fibrous tissue, the dura. Below, the layer of dura passes through the foramen magnum, becoming continuous with the dura that lines the vertebral canal. Two important extensions of the dura create partitions within the cranial cavity. They're the falx and the tentorium. Here's the tentorium. Its full name is tentorium cerebelli. It separates the posterior cranial fossa from the rest of the cranial cavity and separates two major parts of the brain, the cerebrum above from the cerebellum below. This opening in the tentorium is called the tentorial incisure. The brainstem passes through it. The tentorium is attached along this line on the occipital bone and along the edge of the petrous temporal bone. Its attachment ends at the posterior clinoid process. The upper surface of the tentorium is continuous with the dura of the floor of the middle cranial fossa. In the midline, the tentorium is attached to the other major partition, the falx, which we'll add to the picture. This is the falx. Its full name is falx cerebri. The falx forms a midline partition between the two cerebral hemispheres. Here's its attachment to the tentorium. Along its length, it's attached to the occipital, parietal, and frontal bones. Here in front, the falx is attached to the crista galli. To see the falx in cross-section, we'll divide it along this line. Near its attachment, the falx splits into two layers, leaving a triangular space for the superior sagittal sinus, an important part of the brain's venous drainage system, as we'll see later in this tape. Now we'll move on to look at the layers of tissue that give the brain a protective covering and maintain its special fluid environment. These three layers, the dura, the arachnoid, and the pia, are collectively called the meninges. We've already taken an inside look at the outer layer, the dura. To see the two inner layers, the pia and the arachnoid, we need to add the brain itself to the picture. We're looking at the right cerebral hemisphere. The blood vessels on its surface have been filled with red latex. The surface of the brain is richly folded. An outward fold is called a gyrus, an inward fold is a sulcus. The pia is almost invisibly thin. It's just the glossy surface that we see here. To see the extent of the pia, we'll look at a frontal section. Here's a typical sulcus. The pia extends down into each sulcus and back up onto the next gyrus. Each sulcus contains blood vessels which lie just outside the pia. Each vessel that enters the brain carries a sleeve of pia with it. Now we'll add the arachnoid to the picture. This is the arachnoid. It's a delicate, transparent membrane. Here's the arachnoid again. Unlike the pia, the arachnoid doesn't extend into the sulci. It bridges over from one gyrus to the next. In this specimen, the subarachnoid space is empty. Here, we're injecting water to fill it. Over most of the brain, the subarachnoid space is narrow, but in a few places it's quite wide. Notably here below the cerebellum, here above the cerebellum, and here in front of the top of the brainstem. These spaces are called cisterns. Outside the arachnoid is the dura. We'll add it to the picture. The dura is a much tougher layer of tissue than either the pia or the arachnoid. The dura has almost no attachment to the arachnoid. The dura can be separated from the overlying bone, but is normally quite closely attached to it. Now we'll add the rest of the dura to the picture. Here's the intact dura. These are branches of the middle meningeal artery, which runs in the thickness of the dura. To look at the openings in the dura, we'll again look at it from the inside in an empty skull. The vessels and nerves that enter and leave the cranial cavity pass through openings in the dura. At each opening, the dura forms a tunnel around the nerve or vessel for a short distance. Typically, a nerve or blood vessel runs beneath the dura for a distance between its opening in the dura and its opening in the bone. So the openings in the dura often don't match the openings in the bone. The difference between dural and bony openings is specially marked here in the middle cranial fossa. As we saw in the previous tape, the bone here has many openings. By contrast, the dura here has no openings. The corresponding openings in the dura are either up here or back here. As we'll see in later sections, the central part of the middle cranial fossa is a specially busy area. Let's take a further look at it. In the dry skull, this hollow, the pituitary fossa, is partly enclosed by these four bony projections, the clinoid processes. In the living body, the dura bridges over the roof of the pituitary fossa, leaving this round opening. The clinoid processes are here. The pituitary fossa, which contains the pituitary gland, is lined with dura. Just lateral to the pituitary fossa is the cavernous sinus, which is hidden beneath the dura here. This opening in the dura, which is for the trigeminal nerve, leads into a side cavity under here, the trigeminal cave, which is occupied by the trigeminal ganglion. We'll see more of this busy area later in this tape when we look at the vessels and nerves. Now, we're almost ready to move on to look at the brain. Before we do that, let's review what we've seen of the cranial cavity and the meninges. Here are the sphenoid ridges and the petrous temporal bones, the anterior cranial fossa, middle cranial fossa, and posterior cranial fossa. Here's the dura on the outside and on the inside. Here are the falx, the tentorium, and the tentorial incisure. Here's the arachnoid. Here's the pia. Here are the cisterns. Here are the clinoid processes and the pituitary fossa in the dry skull. Here are the same structures in a dissected specimen. Here's the site of the cavernous sinus and of the trigeminal cave. Now we'll move on to look at the brain. The internal structure of the brain, which is extremely complex, lies outside the scope of this atlas. In this section, we'll look at the main external features of the brain and also at the cavities within it, the ventricles. This model shows the shape of the ventricular system. It's formed by two small cavities in the midline, the third ventricle and the fourth ventricle, and two much larger cavities, the lateral ventricles, which connect to the third ventricle here. It's the third ventricle because the lateral ventricles are counted as the first two. The ventricles are filled with cerebrospinal fluid. We'll see more of them as we go along. To understand the external features of the brain, we'll start with the central stalk, which is known as the brainstem. To look at it, we'll take the rest of the brain out of the picture. Here's the brainstem. It consists of the medulla, the pons, and the midbrain. The brainstem contains tracts that connect the cerebrum, the cerebellum, and the spinal cord. And it contains nuclei that serve basic autonomic functions. It's also the origin of nearly all the cranial nerves. The medulla is cone-shaped. It tapers down to become continuous with the spinal cord. The medulla becomes continuous with the spinal cord here at the foramen magnum. The medulla, the pons, and the midbrain are located just behind the basilar part of the occipital bone and the dorsum celli. The dorsal aspect of the medulla faces almost directly backwards. The back of the upper part of the medulla forms the floor of the fourth ventricle. On the model, this is the fourth ventricle, this is the floor. This arch of tissue is the superior medullary velum, which forms the roof of this part of the ventricle. This delicate tissue, the inferior medullary velum, forms this part of the roof. This cut surface is the attachment of the cerebellum. It's described as consisting of the superior, middle, and inferior cerebellar peduncles, which are somewhat fused together. The ventral aspect of the medulla is marked on each side by these bulges, the pyramid and the olive. Emerging from the ventral and lateral surfaces of the medulla are the filaments of the four lowest cranial nerves, the 12th, the hypoglossal, the cranial part of the 11th, the accessory, the 10th, the vagus, and the 9th, the glossopharyngeal. Here's the brainstem in situ, seen from behind. The tentorium has been removed to give us this view. Here's the cerebellum, divided in the midline. Here's the divided cerebellar peduncle. Here are the filaments of the hypoglossal nerve, making their exit from the cranium. Here are the accessory, vagus, and glossopharyngeal nerves, making their exit together through one opening. Above the medulla is the pons. On each side, the pons becomes continuous with the middle cerebellar peduncle. Arising from the groove between the pons and the medulla are the next three cranial nerves. They're the 8th, the vestibulocochlear, the 7th, the facial, and the 6th, just visible, the abducent. The 5th cranial nerve, the trigeminal, emerges from the upper part of the pons. Here's the middle cranial fossa. Here's the petrous temporal bone. Here's the pons. Here are the facial and vestibulocochlear nerves together. Here's the trigeminal nerve. Here's the abducent nerve. The part of the brainstem above the pons is the midbrain. Features of its dorsal surface are the upper part of the roof of the 4th ventricle, the superior cerebellar peduncles, these bulges, the inferior and superior colliculi, and, in the midline, the pineal body. The 4th cranial nerve, the trochlear, emerges from the dorsum of the midbrain. The midbrain spreads out into these two massive columns, the cerebral peduncles, which connect the brainstem to the cerebrum. Here are the cerebral peduncles in the intact brain. They're largely hidden by the lower parts of the cerebral hemispheres, the temporal lobes. To see the cerebral peduncles better, we'll look at a brain in which the temporal lobe and the cerebellum have been removed. Here are the cerebral peduncles again. Here on the outside of the cerebral peduncle are the medial geniculate body and the lateral geniculate body, which gives rise to the optic tract. Between the cerebral peduncles, the 3rd cranial nerve, the oculomotor, emerges. We'll return to the intact brain. Here are the two oculomotor nerves. Here are the two optic tracts. They meet at the optic chiasm. From the optic chiasm, the two optic nerves emerge. They're the 2nd cranial nerves. Here's the brain in situ, with the right cerebral hemisphere removed. Here's the corpus callosum, which joins the two cerebral hemispheres. Here's the divided cerebral peduncle. Here's the midbrain. Here's the floor of the middle cranial fossa. Here's the optic nerve running forwards beneath the dura toward the optic canal. Here's the oculomotor nerve. Here's the trochlear nerve. The ventral aspect of the brain passes upwards to here, then turns a corner and continues forwards into a complicated area that we'll look at later in this section. Now that we've looked at the brain stem, we'll move on to look at the cerebellum. Here are the brainstem and the cerebellum together. The main functions of the cerebellum have to do with balance, motor coordination, and the control and monitoring of intentional movements. The cerebellum occupies most of the posterior cranial fossa. The tentorium is just above it. To see the cerebellum better, we'll look at it by itself. The surface of the cerebellum is marked by many parallel fissures, some deeper than others. This deep primary fissure divides the cerebellum into a small anterior lobe and a large posterior lobe. A deep groove on the underside partially divides the cerebellum into two hemispheres. These are joined by this midline mass, the vermis, which extends all the way round from the top to the underside. Here are the divided cerebellar peduncles, the superior one from the midbrain, the inferior one from the medulla, and the middle one. As we've seen, the middle cerebellar peduncle becomes continuous with the pons. This cavity in the anterior aspect of the cerebellum is the most posterior part of the roof of the 4th ventricle. That's this part in the model. Now we'll move on to look at the cerebrum. Here's the cerebrum with the brainstem attached and the cerebellum removed. The functions of the cerebrum include the senses of vision, hearing, smell, touch, and spatial perception, and also speech and language, memory, thought, and voluntary action. The cerebrum is formed mainly by the two cerebral hemispheres. These are separated in the midline by the falx, which occupies this longitudinal cerebral fissure. Though they look hemispherical from in front, the shape of each cerebral hemisphere is more complex when seen from the side. In front, this part, the frontal lobe, occupies the anterior cranial fossa. This part below, the temporal lobe, occupies the middle cranial fossa. This part behind, the occipital lobe, lies above the tentorium. The two cerebral hemispheres are connected across the midline by the corpus callosum, which runs all the way from here in front to here behind. The two cerebral hemispheres are connected below by the two cerebral peduncles, converging on the brainstem. They're also connected by the structures of this area, the floor of the third ventricle. To see these connecting structures better, we'll look at a brain that's been divided in the midline. Here's the corpus callosum. This is the cerebral peduncle. The third ventricle is here. Here's the third ventricle in the model. It's quite narrow from side to side. This is the floor of the third ventricle. The surface of each cerebral hemisphere is richly folded. Each inward fold, or sulcus, and each outward fold, or gyrus, has a name. But here we'll name only two, the central and the lateral sulci. This is the lateral sulcus. It's very deep. It extends all the way round to here on the underside. Here's the medial end of the lateral sulcus in the intact brain. The lateral sulcus separates the frontal lobe above from the temporal lobe below. This long sulcus running upwards and backwards is the central sulcus. It's the only one that runs all the way to the medial surface of the hemisphere. The cerebral hemisphere is described as consisting of 4 lobes: the frontal, temporal, and occipital lobes that we've mentioned already, and the parietal lobe. Between the frontal lobe and its neighbors, the central and lateral sulci form natural boundaries. The other boundaries are somewhat arbitrary. Here are the 4 lobes on the medial surface: frontal, parietal, occipital, and temporal. The sloping underside of the occipital lobe conforms to the upward slope of the tentorium. Here are the 2 temporal lobes, seen from below. This part of the tip of the temporal lobe is the uncus. The uncus lies just above the tentorial incisure, which is here. Here on the underside of the frontal lobe is the olfactory tract. It ends in the olfactory bulb, from which the fibers of the first cranial nerve, the olfactory nerve, emerge. Each cerebral hemisphere contains a cavity, the lateral ventricle, that's filled with cerebrospinal fluid. The lateral ventricle has an anterior horn, a body, a posterior horn, and an inferior horn. The anterior horn is in the frontal lobe, the body is in the parietal lobe, the posterior horn is in the occipital lobe, and the inferior horn curls downward and forward into the temporal lobe. To see where the lateral ventricle communicates with the third ventricle, we'll go round to a medial view. The communication is here, at the interventricular foramen. To see how the lateral ventricle, the third ventricle, and the fourth ventricle are connected, we'll look at a brain that's been divided in the midline. Here's a midline section through the third ventricle. Here's the third ventricle. This strand of vascular tissue in the roof of the ventricle is the choroid plexus, which produces cerebrospinal fluid. Here's the interventricular foramen opening into the lateral ventricle. The choroid plexus passes through the foramen and continues into the lateral ventricle. The cerebrospinal fluid that's formed in the lateral and third ventricles passes through this narrow passage, the cerebral aqueduct, and into the fourth ventricle. Fluid leaves the fourth ventricle through three openings: the lateral apertures, the right one is in the depths of this recess, and the medial aperture, which is in the midline here. It's easier to visualize the medial opening in this dissection. Here it is, in the inferior medullary velum. The lateral openings are here.